Hello everyone, this is Josef Not here, and I'm very excited to bring you this live stream, which then will also be converted to a YouTube video, because today I am going to redo my very first tutorial, which you can see here, which is called How to Run Your First Simulation in OpenFOAM. I posted that video 7 years ago, and today I'm going to redo it with a fresh view from 2021. So if you're interested in the tutorial, please just jump ahead in the video. If you're watching this at a later time, it will start in a couple of minutes. For now, in the live stream, I will wait for people to join. So in the meantime, so my goal of this live stream and follow-up live streams is to redo exactly these first tutorials, and then we'll see how far it makes sense to go. And I decided that I'm only going to review just one video in a live stream, just to have more time and to discuss it. And if you have some questions, then I'm happy to answer those questions at the end of the live stream. So today we are going to take a look at how to run your first simulation in OpenFOAM part 1, and then next time I'm going to take a look at part 2. So so this is the plan. This is kind of a reaction video to my own video, but also a tutorial, because I will follow along in the terminal, and I'm just going to comment on things that changed since then, and then also what I would do differently now compared to 2014 or something like that. Okay, so I hope that my audio is okay, because I'm still not sure whether to use the elevated position for the microphone or this lower. This way you can see more from my, you can see my face more, but I'm not sure about the audio quality. So please let me know whether it's fine or not in the comment section. And also I enabled the sound of my PC, so you should be able to hear my voice in the video as well, so you can just listen to that, so you know what I am reacting to. Good, so this is the plan for today. I will still wait a little bit for people to arrive, and then we can just start with the first simulation. So I'm not going to watch the entire video. I'm just going to skip ahead at interesting points and then just comment on those. Okay, so now there are a couple of people. So if you just say hello, then I'm just going to stop and then just say hello to you. So everyone who is watching live, hello, and also everyone who is watching the video afterwards, which is generated by YouTube, also hi. So I think in this video I'm just going to have one tutorial case, because in the first half I just took a look at the tree case and not the quad cases, so that the quad cases is for something for next time. Tomorrow I'm just going to concentrate on the very first simulations. And okay. I will do, so as you can see, here is the start of the video, and I prepared a couple of resources that I am going to upload to my GitHub account, so you can download it. There was some issue with the Google Drive where I uploaded this MSH file, but now it should be taken care of, but you can also download this from GitHub as well. Okay, so I have a couple of additional files for this Redux version of the first tutorial, so let's see how we progress. So back then I worked at the university. I had this very fancy slide that I set up in Blender. Currently I just have a white title page, so Yeah, so that changed. Hello everyone, this is Josef Notch here, and in this video I will show you how to run your first simulation in OpenFOAM. Yeah, so this is what I just told you. Back then, my introduction was already very similar, but a bit different. I will do it step by step. Okay, sorry. So I will just jump ahead a little bit with about the details. So the goals are still the same as you can see in this video, and we will also extract the velocity at a tilted line as well as the pressure. But I want to show you, this is one of the things that I would change nowadays. I wouldn't do that in ParaView anymore, but rather I would use a function object to do that. So I'm going to show you how to do that. And this function object is in the resources folder, so then you can just use it. Okay, so that's fine. Okay, so then I prepared back then these slides, so we want to learn the case setup, which I'm going to show you also today, how to set up the initial values, how to generate the mesh. But I want to point out that in this tutorial we are not going to generate anything with block mesh or snappy hex mesh or CF mesh. I take Fluent mesh that it comes with OpenFOAM, and I created also a second mesh which is the same geometry, just not a triangulated geometry but a quad mesh, which I created while I did my postdoc here at the Johannes Kepler University, but that's something for next time. And we will take a look at those three meshes today. The first, the tree mesh, and then the next live stream quad mesh and the refined quad mesh. And I want to post-process it in ParaView, but also, as I mentioned, I want to show you the possibility to post-process with a function object as well. Okay, so that's it. Yeah, so we are going to use the solver IcoFoam, which is a very simple solver. It solves the transient Navier-Stokes equations for Newtonian fluid. So it's incompressible, it's transient, it's laminar, and single phase. Okay, so the equations, I guess you already know these equations. It's the continuity equation, which conserves the mass. So because it's incompressible, it's just the divergence of the velocity is 0. And in the momentum equation, you have the temporal derivative, the divergence term, then the pressure gradient, which drives flow, as well as the stress tensor, where you have your viscosity term. And a very, very important point, and I cannot stress this enough, I did that in previous videos, but also in this case. So whenever you see in an incompressible solver in OpenFOAM the field P, it is not the pressure in Pascal, but rather the pressure divided by density. And you can see why. So in the Navier-Stokes equations, here you would have rho times U, and also here you would have rho. But since we assume an incompressible flow, which means that the density is constant, you can divide by the density. But in the pressure gradient term, there is no density in the original Navier-Stokes equations. So you do have there 1 divided by rho, and OpenFOAM combines the pressure with this density into one variable, which is the P. But don't forget that, especially if your density is very high and not around 1, then you have to during post-processing multiply your p-value in order to get the correct pressure in Pascal. Okay, so that's it. Yeah, so this is just what I just told you. And isothermal, very simple. The very simple reason is because we don't solve any equations regarding the temperature. And we don't directly solve the continuity equation as well, or the Navier-Stokes equation. We use the piezo loop now in the standard OpenFOAM solvers. It's called Pimple loop. And there is not a lot of difference, one small numerical change in the pressure in the preparation of the pressure equation is there, but we solve the so-called piezo loop in order to solve it. So we not only solve the Navier-Stokes equations, we derive a pressure equation out of it. And for more detail, please take a look at the PhD thesis of Professor Jasak as well as Henrik Rusche, because they describe this very well. Okay, so that's the introduction. And yeah, so in this very first tutorial, I was using Ubuntu. That was the day when Windows sucked. Regarding Linux programs, now as you can see, Windows can run Linux programs, and now it is very simple to run simulations in Windows 10, and then you can also use fancy software like Microsoft Word without having to use Wine and stuff like that. Okay, so the point that I wanted to, that I did here is that you can use the Nautilus, or in Windows it's called Explorer, to copy around just like you would do in Windows, but you can also use the terminal. And I'm going to use the terminal here, but you can do that also. But you could copy and paste using the Explorer. Okay, and so our goal tutorial here is the elbow tutorial, because it is a very simple tutorial, and if at least when I started, this was the very first tutorial that I did for Fluent, so this is familiar, and you can see more than in just the cavity case. So I really like this as an introductory tutorial, so this is what I'm going to use. So back then I used OpenFOAM version 2.3. Since then a lot has happened in the OpenFOAM versions, but not regarding IcoFOAM. Fortunately, the case setup is very similar, if not the same. So what you usually do, you copy an existing tutorial and then you only work on that copy, and you don't modify the existing tutorial because you can break it. So this is what I am doing here. I just copied it and called it elbow try for triangulated mesh. And this is also something that I'm just going to do here. So I have here my folder where I have my resources, and I'm just going to copy this from my tutorial. So copy, and from my home, and I'm going to use OpenFOAM version 2012 because I was lazy and I did not install the recent 2106 yet. But the 2106 will work as well because in IcoFOAM not a lot has changed. So incompressible IcoFOAM and then the elbow tutorial. So the path is the same as it used to be back then, just the version number change. So nothing fancy there. Let's just copy it here to the elbow tutorial, and now I'm just going to make a copy called elbow underscore tree, and I'm going to go into elbow underscore tree, and here you can see that we have 0 constant and system, and we have our Fluent input file, which is called MSH. So if I just open it up, it is just a certain format where you have your nodes and then you have your elements, your triangulated elements, and then also here you have your boundary name. So here you could even change the name of the boundaries, but forget it. Usually in OpenFOAM you're running Snappy Hex Mesh, CF Mesh, or Block Mesh. This is just here in this first tutorial where we don't want to worry about meshing. Just the simulation. Okay, so what did I do after this in 2014? And I will do a second case and a third case. Okay, I'm doing that in the next live stream. And I will call this elbow underscore quad. No. Okay, elbow quad, and now I am in. Yeah, so that's something for the next live stream. Now I am in elbow tree, and you can see that I have 0 constant system, then all clean and all run scripts, and then this elbow.msh. I have also this in the newest version. cases. Case let's delete them. Constant. Yeah. So exactly, we don't need the scripts. We will run everything by hand. And what I would now change is, in order to visualize the results, I really like to create an empty text file which is called open.foam. So I'm just going to open this text file with nano and save it, or you could just type in touch space open.foam. That creates also an empty open.foam file, and we can use that later on for ParaView to visualize the results. Okay, then what's the next step in my video? Okay, so we are taking a look at the initial files. Okay, very good. So for that, I am just going to go here and open them up in Notepad++. Okay, so here we have the file, and nothing really changed since then. So I talk about that in the video, and I can talk about that here. So for P, as I mentioned, is the pressure divided by the density. And you can see here in the dimensions, these dimensions are the power numbers of the 7 SI units. So this is kilogram to the power of 0, and meters to the power of 2, second to the power of -2, and Kelvin to the power of 0. So which is then meter squared divided by second squared. Okay, so these are the units, and the last three are mole, candela, and I always forget the last one, ampere, yes. So yeah, and then these are the dimensions. Then we have the internal field. So here we initialize all the cell values. So if we will divide up our geometry into small cells, and we initialize the pressure in each of those cells with a value of 0, so atmospheric pressure. Here we consider the relative pressure. We could also initialize a very long list of numbers, but what's the point? We want to calculate it, so we start with 0. This is usually what you do. You can also add here 10 to the power of 5, so the absolute pressure, but it is rarely done for incompressible simulations. So 0 is the reference pressure, and then we calculate the plus minus value. Okay, so typical pressure boundary conditions being used here. So at the outlet, maybe I should create the geometry first. Okay, so let's just import Fluent Mesh. No, let's just use version 2012, and then Fluent Mesh to foam, and then elbow. Yes, so this created the mesh, and now I can go and open up my results, or not the results, the mesh itself. So this is the mesh, just like you see in my video from 7 years ago. And now, so here on this edge we have an inlet, here we have a second inlet, and here we have an outlet. And at this outlet, so let me just show you here. I just color the faces according to their face numbering. Okay, so this blue region is our outlet. So there you usually at each outlet you fix your pressure because you assume atmospheric pressure there. And everywhere else we use the so-called zero gradient boundary condition, which you usually select at boundaries where you fix the velocity, so on walls and on inlets. And as you can see, on wall 4 and velocity inlets 5 and 6 and wall 8, we use the zero gradient boundary condition. There is a fancier boundary condition called pressure inlet outlet velocity, but that's something for the future. For simple geometry, zero gradient is more than enough. And how to explain zero gradient, I really like to use here paint. So here we have a cell, and then the cell has here the outlet surface. Okay, so this is one of the cells here at the top. So it really should be a triangle. So okay, to be correct. Okay, now I have to somehow, no, let's just draw the triangle like this, and then a second line. Okay, to be correct, it's a triangle, so let's say this is this triangle here, and the outlet is the outlet boundary is here, but no, wait, so we want to model. Okay, so that was a brain fart from my side. Okay, so let's take a look at this cell here, and we have the wall here. So I want to then draw the triangle like that. Okay, and we have our boundary. This is our boundary face, the orange one. And here the question is, what is, so we calculate in our simulations the value in the cell center, and then the question is, what is the value on the face itself? And for the zero gradient boundary condition, you assume that the pressure gradient between the cell center and the wall is zero. So what then this solver does, it just projects the cell center value automatically onto the wall. So which means that you don't care what is happening between the cell center value and the wall, so you just neglect the pressure phenomena between these 2 points. This can be done for simple problems. For more complex problems, you have more fancier boundary conditions. Okay, so these are the 2 types that you usually use for pressure, either zero gradient at inlets and walls and fixed value at the outlets. And you have the empty boundary. But first, let me go to the velocity. So here again, you have your dimensions, which is meter to the power of 1 divided by second, so meter per second. In SI unit, you have the velocity. And the velocity is a vector, so you have to define a vector in your fluid flow. So we assume that the fluid doesn't move at the beginning, and then we take a look at what the flow looks like when we start at the one inlet with a positive value of 1 meters per second. So here 1 meters per second, and here we assume +3 in the positive y direction, and then we see how the flow evolves. And again, on walls, so at the inlets we fix, and also on walls we fix the boundary condition. So let me just skip ahead to the, no, let me just skip ahead to the velocity. So I'm just explaining exactly that. And as you can see, back then the syntax was a bit more complex. So on walls we explicitly use the fixed value boundary condition also, but with 0, 0, 0. Now this no slip boundary condition is exactly that. Fixed value 0, 0, 0 is just less to type in. So it's just for lazy people like me, fancier boundary condition. So this is also fixed value, fixed value, fixed value. So where we use zero gradient in the pressure, we used fixed value in the velocity. And where we use the fixed value for the pressure, here we use also the zero gradient. So the same assumption is correct. So in these triangles which are connected to the outlet, we don't care what happens with the velocity in between the cell center value and the outlet value. And now I mentioned the pressure outlet velocity here as a fancier boundary condition. Of course, it's the outlet boundary condition. You can use inlet outlet, pressure inlet outlet velocity. Here it is, what's the pressure? Fixed flux pressure is the fancier boundary condition that you would use for the pressure. So sorry that I talk too fast. Okay, and then there is this empty boundary. And now what is this empty boundary condition? So this elbow case is a 2D case, but in OpenFOAM nothing is 2D, everything is 3D. So in order to have a 2D case, you have to create a 3D geometry and then put one cell in the third direction, which is the Z direction. So this is what I did back then for Fluent. So I extruded this by one cell in the Z direction, and it is important to then combine the front and the back face of your geometry into boundary. Here I call it front and back planes, and these have the type empty, and if these types have empty boundary condition, then OpenFOAM knows that it doesn't have to solve the equations in the Z direction. So it only solves X and Y direction equations for the velocity. Okay, so this is the empty boundary, and this was created for the mesh. In boundary, you can take a look at the type of your boundaries. So wall 4 is a wall, velocity inlet is a patch, which is an inlet, also a patch, outlet is also a patch, and wall 8 is also a wall, and then the front and back planes are empty. So this type has to be the same as in the initial conditions. If you have here patch and then here empty, then you will get an error message. And so for this simple simulation, whether you use wall or patch doesn't really matter. This wall type is very important for turbulent simulations if you want to use wall functions, because those only work for type wall. Okay, so that was it. Let's just go back to my video. So this is the velocity here, and then, okay, now we go further in our case setup. So in 0, we have our initial conditions and the boundary conditions. So initial conditions, I mean that we initialize the pressure with 0 and the velocity with 0, 0, 0. And the boundary conditions are here, these boundary fields that I just talked about. So this is what you have in 0, and then in constant, you have your mesh, which I just generated with the command fluent mesh to foam elbow.msh. So this imported the mesh, and we have another file called transport properties, and this is nothing else than the kinematic viscosity, and it is constant because we are dealing with a Newtonian solver, and we assume the kinematic viscosity to be 0.01, which is a very high viscosity, but oh well, this is also a simple tutorial. Okay, so that's it, nothing fancy here in the transport properties. Yes, so back then boundary.org was in here, so you can forget that. Okay, so now in system we have 4 files. So we don't want to convert then the results to Fluent, so I'm just going to delete this. And here we have these 3 files. So in FV schemes you have the discretization schemes, which I will talk about in a later tutorial. So we just use the standard values. In FV solutions, we can define the matrix solvers for the partial differential equation, for the matrix equations, the tolerances, and also how many correctors we want to solve. So maybe let's come back to this once the simulation ran. Okay, so important is here the control dict where you set as your simulation setting. So this is the control center of your simulations. What you can change here is, for example, the end time. I do want to run this until 70 seconds, not just the first 10 seconds, because then you can see more here. And the delta t is fine, so we do not adjust the time step for now. we can change the right interval, and since we use the right control, which is called time step, we also define here the number of time step after which we want to save. What does this mean? So we have so save interval equals 20 times delta t, which is 20 times 0.05, which is 1 second. Okay, so we will write out every second. So it is a bit more complex. We could just write. I'm not sure whether my stream crashed or not. Yeah, so possibly my stream just crashed. I hope that everything is fine here. So I think I talked about control dict. Yes, so I hope that the stream didn't really cut me off. So I talked about control dict and the entries here. So the end time, delta t, and then the right interval. Okay, so if you had some problems with the live stream and the video is broken at this point, just let me know in the comment section and I will reiterate this part in the next live stream. So sorry about whatever happened here on YouTube. I hope it worked. Good. So next step in the simulations is, yeah, so this is what I just talked about. Okay, 75 was what I wanted to. So not just 70, let's just run until 75, just like here. And yes, so that's fine. And now I show you the solver itself. Okay, we can take a look at the solver. Also here, I'm just going to go in the terminal to the application solvers incompressible IcoFOAM. So here the same files are present. So in IcoFOAM, we have a bit more of an information here on the equations that are being solved. So these are the exact equations that I just showed you in the video. And also here it says kinematic pressure. So here the documentation is a bit better than back then. And then
the mesh and create.
Okay, no.
You include create fields.
Yes, so how the simulation is being run is that first you create the time in your simulation, you load in the mesh, which are these files in constant polymesh. So out of these, a mesh is created by the solver. It reads in the piezo settings, which are the settings here. So it reads in these two numbers, and then it loads create fields. So let's just take a look at what create fields is. Create fields loads the transport properties and the constant viscosity, and then it loads the pressure field, which is 0 with the correct boundary conditions, and the velocity field, which is also 0 with the correct boundary conditions. And then it creates the so-called phi, which is the flux. Phi is the interpolated value of the velocity onto the cell faces. So if I just go here to my very simple example here, so we have a velocity in the cell center value, and we need a velocity on the face values, internal, no, that's not. On the internal face values, then you interpolate these values from the cell center onto the face centers, and how this is done, this is then given by in FV schemes, but from this interpolation is being done, and the velocity is multiplied by the face area, and then this is the so-called phi, and this is then used for the equation. So not the actual velocity is being used, but this so-called phi, which is calculated out of the velocity. Okay, so then a couple of additional values are used if you don't have an outlet, but we do have an outlet. Okay, so then we load in the viscosity, the pressure, the velocity, and this phi value is being calculated, and then we start our simulation, and then we have this entry time equals, and then a time step, and then we solve the Navier-Stokes equations, and then we solve a pressure equation. So this is the Navier-Stokes equations where we have the pressure gradient, and then we solve, and here you can see the phi value. So this is the first u in the Navier-Stokes equation, and the second u is the actual velocity. And then we solve a second pressure equation. As I mentioned, check out the PhD thesis of Professor Jacek for more information on that. So we solve the velocity and the pressure, and then we iterate. And then once we are satisfied with the results, then we go into the next time step. So here we calculate, so first we calculate the velocity with the Navier-Stokes equations here. And then we solve a pressure equation with the updated velocity. And then from this updated pressure, we explicitly calculate the velocity. So it's a three-step calculation. So velocity, pressure, velocity, and then we iterate over that, and then we go to the next time step. And whenever we want to save, then we will save at the end of the time step. Okie dokie, so this is the source code, a very simple source code. This is exactly what I was talking about here. So yeah. Okay, now we change to our terminal. Yeah, so I already did that. So I already set up my elbow tree. I also already created the mesh, and I also talked about the boundaries. So now and I also showed you exactly that in ParaView, so we can skip ahead. Okay, maybe what I didn't show you are the walls. So the pressure outlet is, as I mentioned, this phase. Then we have our inlet here where we enter with 1 meters per second. Then the second inlet is here in the bottom where we enter with 3 meters per second in the Y direction. And we have wall 4, which are these boundaries, and then we have a wall 8 here. So this is given by OpenFOAM. This file has been around now for decades, I guess. So this is not something I created. This comes with OpenFOAM. In the next live stream, we will take a look at my version of this geometry. Okay, and yeah, so the characteristic is that this is a triangulated case. Okay, then let's go back to the video. Yeah, and now I run the simulation. Okay, so let's so we already imported the mesh. Now all we have to do is run icofoam. So now this runs. This takes a little bit, but it's not very long, so you can run this in Ubuntu or in the Windows subsystem for Linux. There is an installation video on my channel how to install OpenFOAM in native Ubuntu, and also how to install it in Windows 10, so check it out if you have not installed it already. And now we can just go into ParaView and refresh the simulation results. No, it's better to just reload it. Okay, sometimes this works, sometimes it doesn't. Okay, now we have 75 simulation results here. And now, if I go to the very end and show you the velocity, so these are the simulation results. You can play it in ParaView if you want. You can also visualize the pressure. Here in this case, the pressure is not very, it doesn't tell a lot. The velocity is more important. So yeah, so what you can see is that this low velocity fluid mixes with the high velocity fluid, and then here you have a stream of higher velocity, here lower velocity, and here you can see the mesh, which is bad, and in the next live stream I will show you how the results will improve with a quad mesh. But what I want to show you is now the output, because this is important, and in comparison with the source code, because I did that in my previous video as well. So in a time step, so let's just go to the second last time step. So it says time equals, so this is this entry and then the current runtime, and then we solve the Navier-Stokes equations. And as you can see, we are solving ux and uy, not the z direction, because we are using the empty boundary condition with the smooth solver. And what does this mean? We used here in FV solution for the velocity, we used the matrix solver called smooth solver, and we have a tolerance of 10 to the power of -5. So we iterate the equation from the initial residuals to the final residuals in order to go below 10 to the power of -5. So we only need one iteration for the solution of this matrix equation. So this is very fast. And in the y direction, we don't even have to solve it. So at the previous time step, I'm sure that we also had to solve. Yeah, so for example, at time step 56, we had to solve also in the y direction. And then, as we could see here, then after this time loop, we are going into the piezo corrector and then the non-orthogonal corrector, where we are solving the pressure equation. And as you can see here, we are solving the pressure equation 3 times, and then we do it again 3 times. But the difference is that we solve with the Navier-Stokes equations, then we solve these pressure equations 3 times, and then once we solve this, then we calculate the velocity explicitly with the updated velocity. So we solve for the Navier-Stokes equation, we have an updated velocity. Then we solve the pressure equation 3 times with this updated velocity. Then after the 3rd time, we explicitly calculate the velocity without solving any partial differential equations. And then we go with the updated velocity again 3 times into the pressure equation. And as you can see, this initial residual of the pressure is nicely reduced. And here in the last iteration, we don't even have to solve the pressure. So with the updated velocity, this pressure equation is fine. And where did we set this? This we set in FV solution. So this n corrector 2 is the number of corrector 1 and corrector 2. And the non-orthogonal correctors are the numbers of iterations within these n correctors. Now, we specified 2 because you always solve at least once. So this n correctors is the number of, the number of additional pressure equations. So if you set 0, then you will solve the pressure equations once. If you set it to 2, then it's 1 plus 2, so it's 3. So these are the settings. So again, Navier-Stokes, pressure, and then the explicit velocity calculation. And then you iterate over it, as you can see here. And then you have the Courant number, which is 0.5. So I'm not going to talk about that. That's something for later, for stability reasons. I just want you to understand that this is how you solve a time step. And if you have stability issues, then this is exactly where you can improve your stability. So you can see that between the n correctors, the initial residuals, which means the change due to a new velocity update, is a lot smaller. So here it was 10 to the power of -4, here it was 5. Let's take a look at the last time step. So it's 4, and then it's 10 to the power of -5. So if we used here an n corrector of 10, so 10 corrector iterations and then 3 times the pressure equation, then you would see how these initial residuals in each n corrector would decrease and decrease. and then the results will be more accurate. But the question is, what is good enough for you? Because with that you increase your runtime. So by increasing these n correctors, you can improve your stability, but you also improve your runtime. So it's always a trade-off between accuracy and runtime. So it's better, if you have no idea what to use for your problem here, it is better to have a higher number and then have of number of iterations of 0 at the later iterations. And then you can see if you have a lot of 0 number of iterations at n corrector iteration number 10 or 9 or 8, you have only number of iterations of 0, so you don't have to solve your pressure equations with an updated velocity because it's the same. Then you can reduce the number of correctors. But if you see that you have a number of iterations of 500 or 700, and even in the last iteration you have 700 iterations, then maybe it's a good idea to increase the number of either n correctors or non-orthogonal correctors. This is something for you. And then another point is here the tolerances is the tolerance is what is then good enough for final residuals. So for the pressure we use 10 to the power of 6 and 10 to the power of minus 5 for the tolerance, and the relative tolerance is 0, so this is not used. And then here a relative tolerance of 10 to the power of 0.05 is being used. So this tolerance is the tolerance that you want to reach at the last iteration. So this is below 10 to the power of minus 6. And then this relative tolerance is then the relative tolerance in the first two iterations. So it's a bit confusing, but just remember that the tolerance here is then the last value that has to be reached in order to finish the third non-orthogonal corrector. Okay, so that's it. Let me just see what I talked about in the video, because this is pretty much the first part of the video. Yeah, so maybe, okay, so that is correct. So while running the simulation, it wrote out 75 folders, and in those folders we have some result files. Phi is, as I mentioned, this flux through the surfaces, but this is not something physical. But if I just open up the results for the pressure, we have now a long list of 918 entries. So we have 918 cells. So if you want to count through, these are 918 cells, and then each cell has a pressure value, and each cell has a vector for the velocity. Then in the very bottom you have still your boundary conditions, but this is now what changed considerably compared to the initial conditions, that the field is not uniform anymore, but rather is a non-uniform list of scalars. And here for the velocity it is a non-uniform list of vectors. And this is being saved in OpenFOAM. So OpenFOAM results look like this, but it's difficult to do something with a long list of velocity and pressure values. This is why you load those results in ParaView, and this open.foam file tells ParaView to look in those subfolders for files like P and U, and then ParaView correctly loads in and then correlates the mesh with that long list and then correctly visualizes that. Yeah, so this is what I'm talking about here. Yeah, back then this was a bit different. Yeah, and then the results are the same, so nothing really changed. So if we compare 2012 with version 2.3, it's the same, almost the same. Yeah, almost the same. So I can see here a little bit of a difference, but this may be also ParaView version. but there are no major differences here. Okay, so yeah, so now I just started the elbow quad tutorial, but I think I will wait with that until the next live stream, and then I will just recapitulate what I just did in this tutorial, just show you the results, and then use my elbow quad mesh here, and then show you the differences between the different meshes, and then I will also show you how I would use function objects to extract data from the simulations rather than using ParaView. Okay, so that was what I wanted to show you in this first part of the simulations. I hope that you understood how a simulation runs. So it is actually very, very simple to run this simulation. It is just copying the elbow to a second folder, and then all you have to do is execute fluent mesh to foam and then the input file, and then change the runtime from 10 to 75. This is step 2, and then run icofoam, step 3. So you can run this simulation in, I don't know, half a minute, but I just wanted to explain it in large detail, so this is why I took here at least 45 minutes explaining what is happening. And I hope this helps. Now I did show you some changes regarding 2.3, but these very basic solvers didn't really change in the last years. So I'm very glad, because that first tutorial is still valid that I uploaded 7 years ago. But as we progress with the tutorials, especially then turbulence modeling changed a lot. So an updated version really does make sense. So this is what I wanted to show you. I don't really see... guys, somehow the chat disappeared. So sorry I didn't see your your comments. So hi Salih, hi Andre, hi Bazar, hi Patom Pong, sorry for butchering your name. Hi Prashi, hi the guy from Taiwan, hi Brandon, hi Irfan, hi Angel, hi Roham. I just go through your comments here. Okay, the video is not very clear. So yeah, there were some issues with the video in the middle. I hope that this cut in the live stream was not very bad. My Linux installation file don't have the elbow mesh or cavity mesh. Do I need to run block mesh? No. So Prahi, so this elbow mesh is located in your OpenFOAM installation, in tutorials, incompressible, and icofoam elbow. There you have this elbow.msh file. And I also have the download link here in the description box below for the elbow_quad msh. So there is a Google Drive. This didn't work for some, Google did some updating with the link, so this didn't work. Alternatively, you can also go to my GitHub account and download the MSH file there. So it is also here, so you can download it, go here, and then row, and then save as, and then you can download it. So this is how you do this. So I hope this solves this. Hi from Taiwan, hi from Austria. Hi guys, everyone, thanks for this tutorial. I'm so interested in using OpenFOAM. So Irfan, please check out my tutorials and also follow up live streams. I'm going to update these tutorials in the next live streams. I learned a lot, so I'm sorry guys, because I was watching the chat, there was nothing, and for some reason it disappeared. Rohan, I learned a lot from your videos. Now it is so cool to meet you live. I'm glad. that you learned a lot. Jacek, hi, I'm watching in Ireland, so hi to Ireland. And Carol, oh, which university are you teaching? So currently I'm not at the university anymore. I used to work at the Johannes Kepler University in Linz in Austria. Now I have my own company and I'm running CFD projects for companies mostly, but I'm also active on YouTube and also at the conferences, workshops, and I also am involved in the tutorial collection in wiki.openfoam.com, as well as the new OpenFOAM journal. So currently I'm not at the university, but I do also academic stuff. Okay, so yeah, so that was the last question. So maybe the OpenFOAM journal, let me show you, we have the first accepted publication. So it is very exciting news. So here it is, full papers. You can just go here, and if my internet wasn't so slow, then yeah, here it is. Then you have the abstract, and then you can download the PDF and also the case files. Don't forget to register, because then you won't be able to download it, but you just have to register with your email, and then you can for free download the PDF of our first publication in the OpenFOAM journal. So very excited about that. Okay, so Felipe, hello, will there be a tutorial later on discretization schemes? Yes, if you go in the CFD Basics playlist, there is a tutorial on that, so this is something in the future live stream that I will cover. Hi, Professor Nudge. I'm not a professor, thank you for the promotion. I are postdoc at TU Munich. Cool. It's really great to learn CFD from you. Thank you for your effort. Thank you for your nice comments. So thank you for the promotion to professor. But I'm just Dr. Nudge, not professor. And Jacek, have you got a website of your company? I do have euleriansolutions.com if you're interested. But solutions.com. Yeah, so this is my homepage. There are a couple of things, tutorials, CFD solutions, and my publication list, which I should update because the last one is from January and I did some publications since then. But yeah, so here you can take a look at my company and a little bit about myself. Okay, so this is it. So I hope that you liked this first part of the tutorial and that you could learn something in addition to the tutorial from 7 years ago. So next time I'm going to continue with the second video of the first simulation to the second part, and I'm just going to show you how I would do the post-processing nowadays. So there is going to be at least one small change compared to version 2.3.0, but let's see about the live stream. I'm not sure whether it's going to be next week or in 2 weeks. I will let you know on LinkedIn, on Twitter, and also in the community tabs. So make sure to subscribe to my YouTube channel, or you can also follow me on Twitter or LinkedIn in order to get the latest news regarding my uploads. Okay, so this is where I want to stop my live stream at this point. So thank you guys for watching. Again, sorry about the chat. I don't know why it disappeared, but I'm glad that I found out that it disappeared, and I hope to see you next time.